Hey guys, let's talk about acceleration. So first we want to define acceleration, and the official definition that you'll want to know is that an acceleration is any change in velocity over time. So that could mean any one of three things. The object could be speeding up, it could be slowing down, or it could be changing direction. And all three of those are considered an acceleration in physics. I know in everyday life we talk about accelerations and decelerations. In physics, all of it is an acceleration because all of it is a change in velocity of some sort. We're going to focus on speeding up or slowing down in this unit, but eventually we'll get to changing direction. So the basic reason that changing direction is an acceleration is just that velocity is a vector, and vectors have direction associated. So if I change any part of velocity, if I change the number or the direction, either or both of those are considered accelerations. We have a couple of equations that we're going to look at to begin with. So the usual average acceleration equation is this one, where you have acceleration, and we measure acceleration, let me come back to that, equal to final velocity measured in meters per second minus initial velocity, also measured in meters per second, divided by time measured in seconds. Hopefully you know from the last unit that when we see a VF minus a VI, or a final minus initial, that gives us the delta sign. So delta V is a shorthand way of writing VF minus VI. Okay, so when we have meters per second over seconds, that ends up with giving us a unit of meters per second squared, or sometimes you'll see it written as meters per second per second. Those are both the same thing. Okay, so acceleration is a change in velocity over time. Therefore, it's going to be measured in meters per second divided by seconds. This equation is really handy if you're calculating acceleration, because you've already got acceleration by itself, right? But sometimes you're going to need to calculate the velocity, maybe the initial one or maybe the final. And so we can rearrange, we can manipulate this equation a little bit to isolate VF and VI. This equation says VF, or final velocity, is equal to VI, or initial velocity, plus acceleration times time. Acceleration and time are multiplied, and then you add that to the VI, and you can use that to solve for VF or VI, actually, just depending on what you need. We're going to practice a lot in this unit how to know when to use which equation, and so we're just going to kind of baby step our way in here. We've got two different equations, and we're going to try to think about which ones make sense for our problems. In this first problem, we have a car speeding up and we have a truck speeding up, and we want to know the acceleration of each vehicle and which one has more acceleration. So in a problem like this that's kind of complicated, first thing you want to do is just split up your objects and calculate them separately. So for givens, numbers that were given in the problem, for the car, we have a time, it said that in 5 seconds. Delta T, of course, means time. It says the car increases its speed from 50 to 65 meters per second. So 50 is our initial velocity, and then final velocity is 65 meters per second. And that's all we know about the car. Our unknown is what we're going to look for, and so that's the acceleration in this case. So since we're looking for A, we want to use the equation that says A is equal to VF minus VI over delta T. I can plug in my numbers to solve for that. So I had 65 minus 50 over 5 seconds. 65 minus 50 is 15 divided by 5. So I get an A of positive 3 meters per second squared. We're going to spend more time on figuring out directions for acceleration in the coming days. So for now, go ahead, if it comes out positive, just go ahead and write a plus. Okay, so we did the car. Now we're going to do the truck. So the truck had the same time increment of 5 seconds, so delta t is 5. It says the truck goes from rest to 15 meters per second though. So rest is an initial velocity of 0. That's kind of a hidden given. You have to be on the lookout for words like at rest, started at rest, or came to a stop. Those are always going to be a 0 for v, okay? And then the truck makes it up to 15 meters per second, so VF is 15. We're looking for A. We're going to use the same equation again because A is already isolated. That makes it easier for us. And then we're going to plug in our numbers. So I have 15 meters per second for VF minus 0 for VI over 5 for T. And that gives me an A of a positive 3 meters per second squared. So that's kind of interesting. The car is definitely going faster, right? If we're comparing velocities, the car has a faster final velocity of 65, and the truck is slower because it's only at 15 meters per second at the end of the problem. However, the accelerations were the same. So what's the difference here? It's very common to mix up velocity and acceleration and to treat those like the same thing, but they are not the same, and you have to be careful about that. The velocity is how fast the object is moving. The acceleration is the rate of change in the object. Okay, so it's how much the object is speeding up or slowing down. It is not equivalent to the velocity. Okay, and then our last example here, we've got another car moving in a straight line. They give us a whole bunch of speed changes, and they ask what's the acceleration. So for all problems, we're going to start by listing our givens. They give us a lot of numbers here. So if ever you're not really sure, like, what givens do I even need, think about the equations that you have available and which variables are in those. So for our acceleration equation, we have a final velocity and an initial velocity, and that's it. There's nothing in between. So when we write down our givens, we're just going to write down the initial, which was 35, and the final, which was 50, and we're going to ignore the rest of those numbers. Okay? We do need another given, though. If we look at our equation, we need to know a time in order to solve for this. So if you go back to the equation and read carefully, it says that it steadily increases its speed each second, and then it gives you 3 time intervals. So that means time is going to equal 3 seconds. Okay? So we have our variables, we have our givens. We think about what is our unknown, it's acceleration. We've already kind of chosen the equation that we want to use, so now we're just going to plug our numbers in. So I have 50 meters per second minus 35 meters per second over 3 seconds of time. 50 minus 35 is 15 over 3, and so I get a positive 5 meters per second squared for my answer here. And that is all there is to average acceleration.